Okay, yeah, please, Roberto. Please
Okay,
go ahead
well,
whenever you're ready. Yeah.
Sure. So, well, first of all, thanks for the invitation. It's a pleasure to be here. Mario and me are going to do this somehow two works, canonical metrics on holomorphic current algebroids and gauge theory for string algebroid. And we're going to try to show them in with like from outside, now that we put both of them out. So I'll be talking about, first I will be introducing a system of equations, which is called the Calabi system, which is essential to this work. And then I will do the, I guess, kind of dirty work about the current algebroids. And hopefully I will leave it at a point where most of you will be interested to see Mario's talk next week. So let me start. If I have talked about the Calabi system, so let me warm up by talking about the Calabi problem. So this is something when I started working on this, that I wanted to know somehow what was the story behind this problem. So I went to the origin of the Calabi problem. So the first time the Calabi problem appeared, it actually appeared like this. So this is 1954. Sorry about the, okay, it doesn't want to stay. Whoops. Okay, that's it. So it appeared like this in this formulation. So you have, your real manifold, and at the end of the day, what you want to find is on that, it's actually a complex manifold. You want to find a Keller metric with prescribed Ricci form. Okay, so somehow the only thing it says at the beginning is that you prescribe this Ricci form and satisfies, it has to be a suitable one. So this is why it says it's homologous to 2 pi the Chern class. And it was stated as a theorem. This is the proceedings of the ICM of Amsterdam, I think. 3 years later, the same Calabi showed it now as a proposition. So it was a bit downgraded, but it was still a proposition. And even though it's a bit more involved, the formulation, it's actually the same. So, now, you have Mn now, you say, you just fix a Keller metric and you have with a Keller form, like the omega and your sigma. And now the only thing you do is you say, look, what happens if you change your omega and you do your sigma, and you have a sigma prime in the same cohomology class of sigma? Will you be able to find a cohomologous omega prime to omega such that its Ricci form is prescribed? Okay, and it appears as a proposition, but now things are improving because there was something important there in the proof. There was a footnote. So that footnote, it's here, and it says there is a gap in the proof, And this gap in the proof of this proposition is about this conjecture that any compact Keller manifold admits a Keller metric with any assigned positive differential volume element, So this is to say that if I start with my Keller manifold, and then I fix this volume element, like I say, mu, will I be able to find omega? This was a question. Exists omega such that omega n is mu? So this was a problem of Calabi. At the time, he proved uniqueness.
Roberto, yes. Sorry,
yes.
Just for the sake of curiosity. So this footnote appears in the same paper where he states proposition 1, or is a different paper?
Yes. Yeah. This is also some. It's not in a. Now, this is the proceedings of some conference in honor of Lefschetz. Yeah, I go to, I have, I mean, someone is very interested, I can share them. I have them in a folder, like both of them. So yeah, it appeared like the proposition, but there was this footnote saying, okay, this I gonna state it up to this conjecture. Okay, so there was uniqueness, but there was no existence for this. So and then as you know, in 1977, 20 years later is where existence comes in, and there was just in this paper by Yao, and it is still like in Yao's paper, it is stated still in terms of the Ricci form, but somehow for me this will be the Calabi problem somehow. Okay, and not only for me, actually this is something I found out recently. Calabi himself, like 3 years ago, he wrote about, in a volume about Yao, he wrote about when he met him and how he remembers these things. So this is a story Calabi tells just 2 years ago about Calabi conjecture. Okay, so he calls it the Calabi conjecture, and actually he states it in the form I like if in any compact Keller manifold of another Keller metric, you have another Keller metric whose volume form is any given. Okay, so this is actually the way he remembers it in 2019. I mean, he's already like 93, I think, Calabi. So this for me will be today the Calabi problem, and yeah, and here so you have some yeah, what he remembers when the proof came out, and how they, yeah, in Christmas they did a seminar to share the proof. Okay, so we have the Calabi problem. Let me now talk about the Strominger, Hall-Strominger system, just to move forward. So in the Hall-Strominger system, I'm going to state in now the manifold. Before I have this M, okay, and here it was just a complex manifold. Now this is for Calabi-Yau, Calabi-Yau manifold. So, and I'm going to call big omega the holomorphic volume form. So I'm going to state the version that is more convenient to me, and then I will somehow say how it connects to another version you may have seen, in case you've seen it. Okay, so I'm going to fix, apart from the Calabi-Yau manifold, I'm going to fix a compact Lie group, and I'm going to have also in its Lie algebra, I'm going to have some invariant non-degenerate pairing, and I'm going to have over P over, say, the manifold. I'm going to just keep the notation M. Yeah. So this principal bundle over M is a principal K bundle. So this Hall-Strominger system, what wants is to find a connection, okay, and the one form is like that. And this is a connection on P. And what are the equations? So if I denote by F the curvature of this connection, so the equations will be the Hermite-Yang-Mills equations. So this one here, then I'm going to ask this omega, this 1-1 form, is going to have like a weakened, if you want, Keller condition. So this is not going to be closed, it's not going to be balanced, it's going to be conformally balanced, which means that I can multiply to be balanced. So balance would be this. Okay, well, this would be closed, so it's not necessarily closed. This would be balanced if this is 0. So if this is 0, without this one here would be closed. So this with this is balanced. So it's going to be conformally balanced. This means that I can multiply there by a function. So, but it was going to be conformally balanced in a special way by multiplying by this norm here with respect to omega. So this actually, I can say what it is here, if you want. I mean, this is just that this thing square multiplying the associated volume form to the 1-1 form has to be, so just a suitable constant to the n, and this is important bit, okay, the real volume form associated to the holomorphic volume form. Okay, so the form has to be conformally balanced in this specific way, and then there is the trickiest equation of all, which is this, say, Bianchi identity, like this has to be satisfied. Okay, so DDC omega, okay, plus, and here I use a pairing because F is at P, the adjoint of P, so I have the fiber is the Lie algebra of K. This has to be 0. So this is a Strominger system. So if you've seen it before in a different way, so it's not, I mean, you may have seen before just that instead of having this term here, instead of taking just one bundle and one connection, so, well, you take one bundle, but you somehow combine two connections, one connection on the manifold, one connection of the bundle. So you may have seen here terms like trace of the of some curvature on a bundle and some curvature of the connection on the manifold, like this, okay? And then you have to add also the Hermite-Young's Yang-Mills equations for these two connections, okay? In case you do it with a vector bundle instead of a principal bundle. And the system also was introduced first on a Calabi-Yau threefold. Okay, so this take it out for now. So what is the Calabi system now? So the Calabi system, I don't want my manifold to be Calabi-Yau. I just want it to be complex. So this is a Calabi system. So a complex manifold. And what I'm going to do is, instead of having, since it's not Calabi-Yau anymore, I don't have the holomorphic volume form, but I want to keep the information, if you wish, of this thing here. So like somehow of a volume form. So I'm going to fix a volume element here, mu. I'm going to have, as before, the same K, the same P, okay? So I'm going to have this P, a principal K bundle as before. And I'm going to fix also a real parameter because we can afford it. I mean, it's also interesting later. So fine, what do we have to find again? We are going to find the same things. We are going to find a connection and this metric, this 1-1, seen as a 1-1 form. And the equations are going to be actually quite similar, but now they are going to be a bit more general because I'm asking the curvature to satisfy the Hermite-Yang-Mills equations. Now, the equation that changes more is the conformally, this type of special conformally balanced equation, instead of having the norm of this capital omega, which I don't have anymore, I'm going to combine it with the norm of, with some quantity that comes this f omega. So let me just say here what it is. So what I do is the difference between these two things, I'm going to call it e to the 2 f omega. So this is a real function. And this is the parameter that I'm going to put here, but I'm going to combine it actually with the L. So I give more freedom. Okay. So before there was a function. That function was determined by omega, capital omega, the holomorphic volume form. So now I have a function determined by mu, somehow, like mu and omega. Okay. So, okay, this is not, okay, now it's going back. Okay. And I have this equation here, and I keep the other equation as well. Did you see? So now I don't need a Calabi-Yau manifold. Okay, just complex. So this is the Calabi system. So the idea of this system is that it's going to be both a generalization of the Calabi problem and of the Halley-Strominger system. Okay, so the way to see that, let me just sketch it. It is a generalization of, so on one hand, the Calabi problem, and here is important, like for me, the Calabi problem, is to find this metric with prescribed volume. So you just have to take L equal 1, and you just take your mu, essentially that thing there. Okay, you just take this. When you have a Calabi-Yau, when your manifold is Calabi-Yau, so you just take the volume form coming from your holomorphic volume form. Okay, sorry, this is the Halley-Strominger system. Yeah, that's what I'm saying. So this is the Halley-Strominger system. Is just when I do this. Okay, this is the easy one because I change here very little. Okay, so you can see somehow that now you can see everything fits somehow nicely. These two is a 2 there. So this is kind of expected because it really is the model of the Calabi system, is the Halley-Strominger system. But on the other hand, when you do L equals 1 and you ask, and there is no bundle, okay, so then you have these two equations here. When there is no bundle, in particular there is no curvature. So your equations, you have two of your equations are these two here. You are conformally balanced like this, okay, and you are DDC closed. So now you can use a theorem by Ivanov Papadopoulos to conclude that actually in this your omega has to be Keller. Okay, but now if omega is Keller, okay, there is something special happening on this f omega, because from omega Keller and this equation here, so if omega is Keller, it is closed. So from this in here, you have that actually f omega has to be constant. But now if f omega is constant, since we have this, okay, this definition of this f omega, so you are virtually done, because now you can get what you want, which is you can get a Keller metric with prescribed volume, because now this is a constant. This in here is a constant, okay? Since it's a constant, you can just send it to the other side and absorb it in omega. Since it's a constant, whatever you get, it will still be closed, okay? So then you get your solution to the Calabi problem, okay? So this gives you, yeah, you can modify, say, you can modify omega. Okay, so this is how the Calabi system somehow unifies these two problems, and also somehow, if you want, you can also see it as a generalization of the Hall-Strominger system to manifolds that are not Calabi-Yau. Okay, so this is some definition we gave with Mario and Carl Tipler. But it's also based, like, this is one of the works is with these authors, and it's also based in some other system that you can find with Carlos Chavasi in the paper on canonical metrics on holomorphic current algebras. Okay, so let me now just keep this system in mind. Okay, keep especially this equation, which is also this special equation, like the hardest one for the Hall-Strominger system. So this was the first part, the Calabi system, and now let me move, once we keep just that system and that equation, let me move to current algebras to make here. Okay, so let me also start like, kind of a soft way, as I try to do for the Calabi system. So let me just start at the beginning of everything. So yeah, in the beginning of all these things, there was just for M a smooth manifold. Okay, there was this object here. This is the Whitney sum, direct sum. I will just put plus Tm plus T star M. And this was where Courant, Weinstein introduced Dirac structures. When you see that this comes with some nice structure on it, which is you have naturally a pairing, which is just given by its quadratic form, is just for x plus alpha section of Tm plus C star M is just this. You have a canonical projection here. Is just x, and the interesting bit is the bracket. So I'm going to write what's called the Dorfman bracket. So Dorfman was actually writing similar problems at the time, and she was the first one to write what I'm going to write, which is the skew-symmetric version of this bracket. Okay, and this object, this bundle Tm plus C star M with these three structures, pairing, anchor, map, and bracket, is a current algebrite. And this means that it satisfies a certain actions. I'm going to just review them very easily. This structure is just that x plus alpha is a derivation of whatever can be derived. So you can derive the bracket, and you can also derive the pairing. And this derives everything. And the second thing is that, okay, we call it bracket, and actually you can make an effort to skew symmetrize it, but it's not skew symmetric. So actually, if you want to write that it's a derivation, you must go for the non-skew symmetric bracket, and then you have this identity here. Okay, so this was end of the 80s, and there was this structure around that later end of the 90s. Liu, Weinstein, and Chu, used to define in general a current algebra. Now I want to move to the beginning of the notice. And I want to move to exact current algebras. So let me just recall, okay, that now you can consider current algebroids that fit into an exact sequence. I'm going to omit the zeros with the anchor map, and here you have the dual of the anchor map composed with the pairing, and you want this sequence to be exact, and you may want to consider all the possible objects of this kind, and you can see that by taking here an isotropic splitting, these are all isomorphic to the same bundle we had before, to Tm plus T star M, same anchor map, same pairing. The only thing is that the bracket may get changed. So actually the structure we saw before, Tm plus T star M is just a special one, the simplest one, if you want. But in general, we may add in the bracket a term. And this term we are adding is for a closed 3 form, a term which is just Ix, Iy, H, and it gets twisted, okay? So, and actually the story, just to, because I'm going to generalize these things in a second, so up to automorphisms of current algebroids, and automorphisms of current algebroids are those maps of Tm plus T star M that are preserving the whole structure, so they will preserve the bracket, the pairing, and also the anchor. So up to automorphisms of current algebroids, you have that they are given by, it's called the Chevera class, which is actually the class of this H, is amazing, H3M. So an H3M, you can see it as the sheaf cohomology of the sheaf of closed 2 forms. So actually, a way to understand this as well is this: if you see a cocycle like this, what you are doing is somehow pasting local models of these ones here with your local 2 form, which are acting as B fields. Okay, the B fields are these transformations of Tm plus T star M that preserve Tm, but they give you an extra term on T star M. So X plus alpha goes to X plus alpha plus IXB. Okay, so next step, okay, is I'm going to this, yeah, we have Chevera, and okay, we know somehow Marco Gualtieri also, yeah, work on this, but actually Marco was perhaps the first person who looked at holomorphic current algebroids. Okay, so I'm adding somehow levels of complexity. So now I want my manifold to be complex, okay? So, and I want also an extension, but now the thing is, this extension, now these bundles are going to be, because M is complex, both the cotangent and the tangent are holomorphic. So I'm just going, as we do usually, is I'm going to consider just the 1, 0, okay? So somehow I move with the actual complex structure, I go to the 1, 0, and now my complex structure becomes just multiplication by I. So these objects, okay, these holomorphic exact current algebroids, which are those current algebroids that fit into this exact sequence. Here you have to be careful with the holomorphic wall, because before somehow the bracket, okay, here I didn't say it somehow. I said that for sections you have this bracket. Okay, now of course, since you are holomorphic, so you have to have the sheaf of holomorphic sections, okay? Because you may want to define this. You have to define it locally. In the smooth case, you can just go global and use partitions of unity. So if you take care of the holomorphic aspects, they all are again isomorphic to T10M plus T star 10M as complex bundles, but not as holomorphic bundles. So this is the thing. So two things may change, okay? So this is true as complex vector bundle, but we have two things that may change. So, I mean, we already see how one thing changed before, which was a bracket. So we should expect a similar behavior now. But the interesting thing is that now the holomorphic structure is seen as a del bar operator. So usually one would think, okay, so in T10M plus T star 10M, so I have this, the diagonal del bar operator. So it turns out that you have some freedom to put something here. So you can put here something in your del bar operator, and this something, okay, has to be some object that it's a 1-0 vector, okay, and should give you a 0-1 form with values in the 1-0 forms. So this is actually 2-1, okay? Yeah. So because I'm eating a 1-0, I'm giving a 1-0, and then I have the 0-1 because the delta bar. So I can twist in general this holomorphic structure on the bundle by this extra term here, and I can also change the bracket. So this is the holomorphic structure, and then also I can change the bracket. In the bracket I can add a term, and this is just another h. Now it has to be a 3-0 form. Why? Because, okay, so it's 1-0, 1-0, so, and I need something 1-0, but I can do this as long as, and here the conditions start, okay, as long as this in d of h30 plus h21 equals 0, okay? So, and again, I could classify them, and up to automorphisms of these objects. So what I get would be like h1 of the holomorphic close to forms, okay? And these are actually, you can see how it is just isomorphic to considering 3-0, 2-1, considering those that are close, and just taking the image of the 2-0-1s here. Okay, this is all well theory, and actually, yeah, perhaps we could call this, and I don't know if we call it in some paper well theory class. Actually, I don't know. So yeah, okay. So from Tm plus T star m, we can twist with an H. We can go holomorphic, and this adds more information. Okay, so this is a direction we can take. Now the thing is, we can go in another direction, and which is, say, an intermediate direction. Okay, so I said here in the beginning, but there are other beginnings. Okay, the thing is that this choice of Tm plus T star m, so is very convenient when you, in the time when Dirac structures were introduced, because you could see presymplectic and Poisson structures as subbundles of this Tm plus T star m when you consider their graph. But okay, imagine I consider a trivial line bundle over my manifold, and now I say my beginning is this bundle here, Tm plus 1 plus T star m. The thing is, it has an anchor map because it has a projection to Tm, okay? It has a pairing as well, so this you can just, I'm going to say, okay, so the anchor map is just X, the pairing is, okay, you have the pairing from before, and you add just the F term, and it comes also with a bracket, so you can just, it's just the bracket of you had before in the current algebroid. And now what you can do is, okay, you can actually from X, you can take also this xg minus yf in order to get a component in 1, and you can also from the components from these functions you can get a 1 form. Okay, so it turns out that this also gives you a current algebroid. Okay, and this when you do something now we can do something similar to what we did for Tm plus T star m, which is twisting it. or the possible. So this is something that, yeah, I would call odd exact current algebroids. And now the thing about this is that if you start with an E, what you do is you can project to some Lie algebroid here, which is an extension of Tm and this one. Okay, so and the kernel of this is T star. So this would be, if you want the picture. I've put it this way because you can also then complete the thing if you wish. You can do this as well. So it looks quite of symmetric. Okay, but for the thing is we are somehow replacing Tm by this extension. Okay, and you can we can wonder, okay, what are all the possible current algebroids of this type? So again, they are all isomorphic to the model, but they get twisted. Okay, and let me tell you how they get twisted. Are isomorphic to the model, which is Tm plus 1 plus T star m, and same pairing, same anchor map, but for the bracket we add some terms. And now for a 3 form which is not necessarily closed and a closed 2 form, you can add to the bracket the following terms. You can add this function, you can add this one form, and you can add also this term here, which is another one form. Okay, and just this is what you would put here. And as you can see, things start to get longer, okay, but you have them all. You can do this as long as such that dh plus f squared equals 0. Okay, and this is a key moment because dh plus f squared equals 0 is quite similar to this in here if you take h to be dc omega. Okay, I mean, if this was a thriller film, I wouldn't say anything. I would just leave it there. Okay, but I'm just doing like stressing that this is a.
Sorry, can I just ask? You say
Yeah,
you're
sure.
allowed to add these terms satisfying this condition. I imagine you want some sort of property of the bracket to still be preserved. You mean you can add these and some kind of property of the bracket still holds or something like that?
Yeah, well, you add these terms. The thing is, you want the properties of the bracket is to be, you want to get a current algebroid. So your bracket, if you want your bracket to be a derivation of the bracket, that means the Jacobi identity and a derivation of the pairing, okay? And you want, if you want all the actions of a current algebroid, all the possible brackets you have on Tm plus 1 plus T star m are exactly these. Those are all the brackets you have, okay? They are all described by 2 form, closed, 3 form, not necessarily closed, satisfying dh plus f squared. And that property, as you say, will make those conditions, those actions be satisfied, okay? This is how you find it. You put them, you say, okay, what is this? It would be something for some HF, you do it, and the condition for something to be equal is that this vanishes, okay? So this is another way of doing it. So it's perhaps a bit more naive, but if you say, okay, I want all the current algebroids satisfying these 2 things, actually these are just all the current brackets, Dorfman brackets, sorry, you could put are exactly the ones having those terms. Okay, so you can also classify these objects. So and the classification goes also along similar lines. So this is say up to like automorphisms. these are also some, yeah, check shift cohomology seen as a check cohomology. And here I put like 2 + 1 forms close one form. So that the thing is now I'm not going to get into this geometry, but if in usual generalized geometry there are B fields, so here there are BA fields, so there are also one forms acting in some way. So when you consider like the transformations which are 2 forms and 1 forms together and they are closed, and you consider the shift of these things, so this actually giving all your classes, and this object here is actually a principal, because this case is very similar to the one I have above, okay? And H3n bundle over the 2 forms whose square is squaring to 0, H2 such that if square is 0, okay? So can classify them in a similar way, and we could do, but we could do a holomorphic picture. Okay, let's keep that. The interesting thing is this variation of your starting point, Tm plus C star n plus something else, and that this equation appears. So this is something that is called Bn generalized geometry, which is what I developed in my thesis. So Bn, because this is a vector bundle, but is also an SO n+1 n bundle, okay, because this pairing has signature n+1 n, and this is actually a real form of SO2n+1 C, and these are the groups of type Bn. So if you want, from this viewpoint, so somehow classical geometry would be kind of n+1 geometry, and usual generalized geometry would be Dn geometry. Yeah. So this is Bn. Yeah. So
could I ask a question?
now, sure.
Could you scroll up just a little bit?
Yes. Yeah. More?
No, that's good. So my question, so for usual exact Courant algebroids, the idea, at least if there's a quantization condition, is that they're the symmetries of a gerb, and the Chevera 3 form is like the curvature or the characteristic class of the gerb. In this case, it kind of makes me think that it's like an equivariant gerb over a line bundle. Is it something like that?
Yeah, I haven't looked into that, but I would be happy to discuss it. Yeah, I haven't looked from that viewpoint. Yeah, into I know there've been like there's been a from the point of view of derived geometry. So like graded manifolds and so on. Okay, it's been interpreted in that way, but somehow, yeah. But I haven't seen it from the point of view the gerb viewpoint. But I would be happy to discuss it. Yeah, actually, if you think it's of any interest. Yeah.
A comment about Francis' question. You need to, I think is what you say, it's an equivariant gerb over a U1 principal bundle, but you need to impose some condition on the class of the gerb, because it's kind of special. It's, I mean, at least in the non-abelian case, it's certainly special. I don't know if maybe in the abelian case there is not.
I mean, there may be something, because for instance, when these people of the graded manifolds do it, if you do it properly, you have to add for it to be invariant under some there was some involution there of something, yes, but yeah, I don't know. I mean, this is if I had to bet some money, I would bet for this extra condition, but it's just a feeling. Yeah, nothing.
What is the meaning of that equation, the dh plus f squared, from the perspective of the equivariant gerb?
That's a question to Mario, actually. because I haven't said the word yerb. So Mario, if you want to take this question about from what you know in the
at least in a pedestrian way, this equation is what allows you to construct the representative of the Severa class upstairs, which is the pullback of H plus some connection wedge F. So yeah, and the fact that it splits into pieces, it comes from the fact that it is U1 equivariant, I guess. But I don't know if there is something more. Yeah, but you can also see it in terms of like years with curving and connection and so on. Yeah. I don't know if this answers.
Okay, thanks.
Okay, so this was BN, which is like the toy model for what's actually the beginning that's interesting for us. So finally, okay, in all these parallel universes of Courant algebroids, we are arriving to the beginning we are interested in. So what's the beginning we are interested in? So I want to generalize, somehow look at this. I'm kind of playing in, I've done it two-dimensional because yeah, it would be a mess to do it three-dimensional, but there are here three directions actually. Okay, here I'm changing the the setup, okay, the bundle. Then you can twist. This is the direction of the twist, but it's also the direction of going holomorphic. Okay, so actually this would be the three directions. So the beginning we are interested in is I'm going down first in this direction, but I'm going to do it perhaps all at the same time. Is I'm going to make my bundle more complex. How? So think that instead of taking just a R here that comes with this pairing, which is this the pairing of the R, and comes just with essentially, I mean, like this bracket. I mean, the bracket between is just trivial. I don't think I have this extra term coming in this Dorfman bracket, but actually this R would be just like an abelian Lie algebra. So you could put here, if you wish, you could try to do that and say, okay, I have some Lie algebra, and then your bracket will play a role here, and it has to be a quadratic Lie algebra, and your quadratic form will be playing a role there. Okay, but I'm going to twist it all over because we cannot do like so many iterations of this process. So with that in mind, let me just straight away consider the following case. Okay, so I talked about the Lie algebra. So actually, I'm going to start here with reductive, say reductive Lie group, and okay, for now, I'm going to keep it. Yeah, okay, I'll keep it. Yeah, I'll keep it now real for now. Okay, so again, I have here it's Lie algebra, and I have a pairing. Okay, like non-degenerating variant, so like say the Keating form, and you complete in the center. And instead of considering a trivial bundle over your manifold, you consider a principal G bundle over your manifold, and what you do is you consider that joint bundle of this. Yeah, okay, so here you have the joint action. Actually, yeah, we call it add, but and then it's capital add there. Okay, so now what I want to do, as you can imagine, is I want to put a Courant algebroid structure in here. Okay, now the thing is the anchor map, easy. Okay, the pairing, have this, I have this, easy as well. The problem is the bracket. Okay, how do you come up with a bracket for this? So okay, so in order to define a bracket, since what you actually need is we need to have, okay, let me see, in order to define actually all the possible brackets, but in this case, since I already twisted the bundle, which is not like this is not a just trivial G bundle, so I will need this information anyway, okay? To define, I'm going to put here all the brackets. What do I need? I need. So what do I need? I need a connection, okay? Theta, connection on P with curvature F, a two form, and I need also H such that dH plus F squared equals 0, okay? So once I have that, I can define a bracket that just somehow, I mean, if you do it step by step, it's not so horrible. If I write the whole formula, it will be quite scary, but here what you'll do now, these are the terms I had before in the initial example. What I can do now is just to put all the combinations. I'm going to put them, and somehow they make sense. They live in the right place. So if I take the Lie bracket now, I take the Lie bracket on the algebra, so I get this section of at P. Of course, why do I want the connection? Because I want some interaction between the vector fields and the sections of that joint bundle. So this gives me another section of that joint bundle. But it may be as well that from a vector field and a section of that joint bundle, I'm able to produce a one form. So yeah, and this you do it with the curvature. Okay, so somehow all these terms are giving you like from two of the ingredients. So another ingredient. There is one more term. This is actually similar to the twice GDF I put before, like this one here. And I have always our friends, like the forms, these ones here, okay? And if you, well, as you can see, at least at this stage, you could check that what I'm writing on the right-hand side lives somewhere in Tn plus at P plus T star M. So, but of course, there are some actions to be satisfied, and yeah, you could check. That's the case, but somehow you can recover if if you want to do it in a simpler way. You could recover from I think it's from Tp plus T star P by reduction. You can recover this object, and then you get the right bracket. Okay, so now I already have here this, like the smooth version, and now I've already achieved the complexity I want in the initial setup, which is Tn plus at P plus C star M. And now I'm going to go holomorphic. So and this already twisted, say, okay. So let me now head towards the objects that will be relevant for us. So I'm going to consider some special class of holomorphic courant algebroids. So let me consider a holomorphic courant algebroid. I'm going to put it as Q, and it has all the things here. Now, for a holomorphic courant algebroid, what I will need is that now P is a holomorph or a G complex. Okay, well, everything complex, like also, yeah, the manifold counts. Okay, P holomorphic, G complex, everything, and also the pairing. This pairing will be complex pairing. So now the thing is, this Q is going to project via the anchor map to T10. Okay, it projects to the holomorphic T10M. But And this is one of the reasons I introduced before this Bn geometry, okay? Now, wherever I put 1 before, I would like to put here, say, at P, okay? So, if I have there at P, actually what I could put here, like Tm plus at P, so this is kind of the Atiyah Lie algebroid of P if you just choose a splitting. So what I'm saying is I want to consider objects Q such that such that they have a map, okay, that comes here to some Lie algebroid, and this Lie algebroid, again, I mean, it has to be this definition to work. This is not just any random map. What I want to consider here is specifically, okay, the quotient by the kernel, like the orthogonal to the kernel of pi, okay? Again, just think the kernel of pi is just whatever is not T10M. So it will be just here, so the orthogonal to the other thing, but the orthogonal to the other thing is actually like I'm deleting the T10M, so I'm actually staying with the T10M and something else which will look like at P, okay? In a second I will clarify this a bit more, okay? I was trying to just play a bit with this thing, so let me call this at Q, and at Q is by definition this kernel of pi, perp. So what I'm saying is I want to consider those objects Q that are similar to this Tm plus 1 plus T star M when 1 is replaced by at P. So the way I do that is by putting a diagram like this. Okay, I say I want those Q that fit into an exact sequences like this, where, and this is the important point, this thing here is isomorphic to the Atiyah algebroid of P, okay, and in such a way that this thing here is isomorphic to the adjoint bundle of P. Okay, so are these, at the end of the day, I'm considering these extensions. Okay, the only thing I can define them somehow just from the Q. I want to give a concrete identification in terms of Q with the Atiyah and Atiyah Lie algebroid of the principal bundle and the adjoint bundle of that principal bundle. Okay, I want to have that identification. Okay, so this thing here, okay, when Q is holomorphic, and I have all these holomorphic exact sequences, and this actually looks very similar to Tm, T star M, and at the P, this is what we call a string algebroid. Okay, so this is string algebroid. Okay, so you can see this sequence as a generalization with much more complexity than of this Tm plus 1 plus T star. So before I gave you several classifications. We remember the Chevera class, we remember this Guattari class, and then I told you how it looks like for Bn generalized geometry. So how are these classified? And these are classified, and I'm going to put concretely by what they are classified. So they are classified by triples, where you have a principal bundle, the principal bundle over a manifold, okay? So you can change if you want the principal bundle, you will have an H and you will have a theta, a connection. Okay, so in this case, well, the P is a holomorphic principal bundle. Now H is going to leave, and look, now we are just getting somehow a combination of what happened for holomorphic, what happened for this Bn. Okay, so you get this thing here, you get a 3-0 plus 2-1 form. And again, this will play the same role. Okay, this will change your complex structure, the holomorphic structure. This will change the bracket. I get a connection. Okay, we saw the connection was necessary to define the bracket even. Okay, so this is a connection and it has to be compatible with the holomorphic structure. So I'm going to ask this to be, these are the connections on P with vanishing 0-2 part. And of course, I mean, I'm just generalizing everything. So I'm going to get all the ingredients. I got this from holomorphic. I got this from the definition here on the left. And I'm going to get the identity that we want to have, which is this thing here, okay? Like if this is the curvature of the connection, so this has to be 0. So I'm going to get these classes, okay? Now, of course, there is an equivalence relation here, okay? This equivalence relation before, for instance, in the case of the Echeverria class is just, if you give me an H prime, you would say just that the H prime has to be H plus dB, okay? So this would be if you classify in terms of cohomology. So now things get complicated, but still it's a combination of the flavors you have before. So now, yeah, I'm just going to put it for the sake of completeness, but you want here, you will want some isomorphism here, some so between those two. You will want also your two form. See, someone wrote in the chat, I don't know if, okay, I'm saying Francis, okay, so that's good for later, I guess. So, what will happen now is that these three forms have to be related not only by a two form, but there is some expression here, but it's very concrete. It's not simple, but it involves Chern-Simons form and all on the connections and the, so there is this, okay? You add this term and then you have this equivalence relation, okay? So this is the classification. This is what somehow is replacing your third cohomology class in the case of Echeverria, okay? So now, these are holomorphic objects, and we can do the same if you want with real, and with real we did it on the left. We can do it also with complex. Now, okay. So this string, okay, string algebroids come in three flavors. So we've seen actually these two flavors. We've seen real.
Sorry, can you just repeat what is the argument of this first Chern-Simons term? Is G?
No, well, the Chern-Simons. This is the connection. Yeah, you are comparing somehow. Theta is a connection on P, so you are bringing it to P prime. And, okay. So this is how.
And in the last term we have G prime.
No, it should be just G. Yeah. Wow.
Okay. Thank you.
That's yeah, very good sight. Yeah. Okay. Because I'm not. My handwriting is horrible at this time of the day. So yeah. So yeah. Yeah. There was a prime too many there. Okay. So the three flavors are the real ones. Okay, which is just here. P will be just, I'm going to take, okay, for a compact group, okay, with compact K. H will be just omega, a real three form. and theta will be a connection on P. We've seen the holomorphic flavor, which is the one I put here, the one I classified. Actually, I want to do it the other way. I want to bring the real to the right for this, and the holomorphic to the left. So because we've seen, so in the holomorphic one, so P is for G a complex group, so which is actually the complexification. The idea is to think about this as the complexification of some compact group, which is the K there. Now H lives in H3 plus 2, 1 is like it's a 3, 0 plus 2, 1 form, and theta, so it's a connection on P. Okay, so now this Q has to be thought of as, well, as I put before, T1 0 plus this at P plus T star 1 0 n. So from this, you can actually go to what we call a complex string algebroid. And a complex string algebroid is, so what should be a complex string algebroid? So a complex string algebroid should be just, you are taking it's just the complexification, okay, of all this stuff. I mean, P is already complex, so you don't worry about that in this case, but it should come with a complex. So actually you have a map, like when you have any holomorphic string algebra, you can just produce some complex one just by taking this Q. Of course, you have to take care of all the brackets, and okay, you have to do it carefully, but you can actually complete. You can. This is the forgetful. Okay, this is, you forget about if you want, about the holomorphic structure of these things. Okay, so the complex. So what you will have is somehow these are given by P is, again, now it's, before it was a holomorphic bundle, so now it's a complex bundle. Okay, again, G complex. Now H will be a complex free form, and theta will be a connection on P. Okay, so somehow what I said for holomorphic, this classification for holomorphic string algebroids, or simply string algebroids, so it applies in the other cases by making these modifications, or where things live. Okay, so on the other hand, I have these real string algebroids, and I can make sense of a complexification map. Okay, so it's possible to complexify here my real, or talk about real forms. Yeah, so this somehow what you have to do is, so just think about it, that you want your E real. Okay, I'm going to call this here like the string algebroid E real. So you want something inside your E complex, and in such a way that, so your Tm, because here is just a real Tm, goes inside the complexification. And here I have this, now is where I should be careful, because here somehow I had this at, of my, these adjoints of P. Okay, so let me say here, this actually is the Atiyah bundle of Pk, the Atiyah bundle of P. Okay, this is not an inclusion, but there is an injective map here. So you can make sense of the complexification, so you can talk about real forms as well. Okay, so in this picture, it turns out that if you start with a holomorphic object and you forget about the holomorphic structure and you get a complex one, and you come here and you ask whether there exists a real form, compact real form, okay? The answer is not necessarily, okay? But those which have a real form. They are a special class, especially relevant for what we do, which are both Chern algebroids. Okay, and these are, by definition, are the Q holomorphic string such that this complex string algebroid admits a real form. Okay, so this will be the class that we'll be interested in, and let me try to get to the end and we'll see why. So before that, I think the only piece of information I may need to conclude should be this chain correspondence. So now I have holomorphic, complex, and compact objects. Okay, so now the reduction to the maximal compact subgroup is kind of like a metric. Okay, and I have this holomorphic structure. So if I have this holomorphic structure, so if I have Q and EQ, okay, now real forms of EQ are, okay, so a real form is like a metric. Okay, so metrics in this sorry, no, I'm putting it in the, no, I don't want to put it like this because the chain correspondence is better to say, okay, I have a complex one and I have a metric. Yeah, okay, that's better. Yeah, yeah, I have EQ, sorry, I have EQ and I have ER. So now the idea is whenever I put, so this should be thought of as a metric, because a reduction to a maximal compact subgroup. Okay, so now the idea is whenever I have a holomorphic structure, okay, this will be in correspondence, and this is a thing with, there is a thing called a horizontal lift on ER, and this should be thought of as a kind of a connection. Okay, so a connection compatible with the metric. That's why it lives in ER. Okay, compatible with metric. So this is an analog of the chain correspondence. Okay, these horizontal lifts are kind of very similar to like lifting TM to ER. So they have to give, they are just subbundles of ER that have the right rank. So the rank of W is the dimension of the manifold, and then they have to satisfy that, yeah, omega with the kernel of pi has to be 0. Okay, so what this at the end of the day is like lifting TM. So it actually fits with the meaning of a connection. Okay, so why am I telling you all this? Okay, so now we have some mathematical objects, these both Chern algebroids, okay, which are a particular type of string algebroids, which are classified by a class of a principal bundle, okay, a 3-form, and a connection on that principal bundle. When that object is real, when I'm talking about real string algebroids, P is a principal K bundle for K a compact group, H is a real form, and phi is a connection on the bundle. So now it comes the time where I come to the system I had before, this Calabi system. So Okay, remember that in the Calabi system, I had P, a principal bundle, and I had theta and omega. Okay, so given a solution to the Calabi system, okay, so the Calabi system is for some principal bundle, and the solution is a solution given by omega and theta. I can produce P dc omega theta, okay? This is, I can produce a real string algebroid, okay? And actually, bear in mind that I'm losing information with the omega, okay? So the omega, here I'm just taking DC omega because I made a 3 form. And I'm not getting just a real string algebroid, I'm getting a real string algebroid plus a horizontal lift. Okay, so now we can somehow see why these objects fit nicely into for the Calabi system, because if this is my H, now dH plus F squared becomes actually dc omega plus this thing I put before, like this, F. Okay, like here I can put it also with a pairing, F, which F equals 0. This equation becomes the equation of the Calabi system. Okay, so for every solution to the Calabi system, I'm getting this real string algebroid. So now, what can I do with this? And I'm getting some, and I will say some things that Mario, I mean, I've already said some things that Mario will describe better next week, more precisely. But somehow now what you could do is you could consider this Calabi system on a particular real string algebroid. Okay, so you can fix the real string algebroid and consider all the possible solutions. What are solutions? So now we have a geometric meaning for that, for those solutions. They are horizontal lifts. Okay, so there will be some horizontal lifts, and one of the things Mario will show, spoiler, is that thanks to all this setting, thanks to the fact that I've been here like introducing all these objects, those can be seen as the zeros of a moment map. Okay, so this gives a moment map interpretation of the Calabi system, and in particular, it gives a moment map interpretation of this Halley-Strominger system. But you can also play with the this thing of the holomorphic string algebra that is associated to the data we have, because I've said here you have a real string algebra with a connection. Okay, so from real to complex, I complexify. Now the connection, the chain correspondence also works in the, like I have it here, okay, because I have this, sorry, this connection, this horizontal lift. Because I have a horizontal lift, I have also a holomorphic structure on my on the complex one. So I can get from a solution, if I get to a real string algebra with a horizontal lift, I also get to a holomorphic string algebroid or algebroids. And why are holomorphic string algebroids relevant? So ER plus horizontal lift gets me to a holomorphic string algebroid. Okay, so now the thing is, yeah, in holomorphic string algebroids, this is something I will say very quickly. So somehow you can play also here with some characteristic classes, and let me just say that somehow in some cases, which are simple ones, but they kind of promising, if we are optimistic, is that there are cohomological objects, logical objects, which we call Epley classes, ensure uniqueness of solutions. Okay, so somehow this recovers one of the features of the Calabi problem, that was that before Yao came to prove existence, it was known, okay, that for suitable Keller classes, the solution to the Calabi problem is unique in that Keller class. So in some cases, you can see somehow small in the paper, in this paper of canonical, even though in a different, with a slightly different setup, but you can see an example where there is this uniqueness in Epley classes, and also in the other paper you can see it in more generality. So it somehow this approach through the string algebroids is giving us the tools to understand geometrically and also somehow to being able to express analogs, okay, of properties we see in the Calabi problem and in the Halley-Strominger system for this Calabi system, which is a generalization of both, and in particular, so also this moment map interpretation. So bottom message is that string algebroids, okay, coming in these three flavors here, will allow us to prove some nice results about this Calabi system. And if you want to see them much better, and so you should join next week when Mario will take it from here and show us about all that. Well, thanks for your attention.
Yeah, thanks, Roberto. Yeah, let's think. Are there any more questions? I guess I have a very naive question somehow, if you know anything about, I mean, I guess these various structures, I mean, they have all these names coming from physics, string algebroid, and this derivation of Hall-Strominger in the first place. I mean, is there a point of view coming from math physics that gives you, for instance, all these different bracket structures? I mean, were they more or less working with these bracket structures under a different name or something like this? Or?
So, sorry, say again the question.
It's not a very well-defined question, but I guess I just wonder the extent to which these various objects and equations, the way they spat out of string theory, if it has anything to do with the way that you sort of capture them in this generalized geometry language.
I think for the string question, I don't know if Mario has something smart to say. I see he answered in the chat, why is it called a string algebroid? So, but
I mean, this, I guess, part of this appears in the theoretic string, but in the generalized geometry language, it was not so clear what to do with this picture. until Baraglia, Hekmati, and wrote their paper, and I wrote my paper on torsion-free generalized conditions. So I think this is one of the very few cases where maybe the math came first, you know. Because I mean, in the exact cases, people have been studying these brackets and so on for quite a while, I think, in relation to generalized scalar and so on. But for the theoretic extreme, was not clear what to do.
I see. Okay. Anything else?
So let me just remember that somehow all these parts, which I put the Calabi system, I put the names, but of course, all these parts of holomorphic string algebras is also the work. I mean, those two works, which apart from Maria and me who are talking, there are two more authors, like Karl Tipler for the second one, and also Carlos Shabazzi for the first one.
Okay, well, yeah, if not, let's thank Roberto again. And yeah,
Okay. Thank you.
look forward to next week.